When we talk about support reactions, we're talking about how to represent forces acting on an object. There's a page in your course packet that goes over a number of different support reactions. Really, that doesn't list all of the support reactions, but most of the support reactions can be broken up into one of four categories. The first one is a cable or a weightless link. So suppose we have an object, and I'm going to draw all of these as beams. In this setup, there's only one unknown, and that's a force parallel to the cable. The second situation is a rocker, a roller, or a smooth contacting surface. In this case, we also have one unknown, and that is a force perpendicular to the surface. Next is the hinge or pin. In the case of the hinge or the pin, we have two unknowns. There's either an X and a Y force, or one force and an unknown angle. Finally, we have the fixed support. In this case, there are three unknowns. There's an X force, a Y force, and an unknown moment. So when you look at your support reactions, you need to think about the number of constraints placed on the system. For example, a cable or a weightless link, if we were to tug in this bar, we'd be able to move it left and right, up and down. We'd be able to try to turn it. The only thing we wouldn't be able to do is pull it away from this point. We couldn't make the cable any longer. So there's one unknown there. Likewise, the rocker or roller would allow us to roll the object back and forth. It would allow us to pivot the object. The only thing it wouldn't allow us to do is to push the object into the surface, so it has one unknown there. The hinge or the pin doesn't allow us to move the object up or down, does not allow us to move the object left or right, but would allow it to pivot. So therefore, there's an unknown X and an unknown Y. There is no unknown moment. Now, if you're curious to know why there's no unknown moment, think about it this way. If static equilibrium is true, and the sum of all moments is zero, since a hinge cannot resist a moment, there can be no moment present there. If there was a moment present there, the hinge would be moving. For the fixed support does not allow vertical translation, horizontal translation, or rotation either, so it actually has three unknowns. Here we have an object supported, and we're asked to find the support reactions. The first step of this problem is to draw a free body diagram, but before you draw that free body diagram, I would encourage you to look at the object and try to determine what the support reactions are acting on this object. So here's our free body diagram. You need a sign convention. You also need to label all forces, angles, and distances. Now we want to try to figure out what the support reactions are doing. So up here at point A was a cable. A cable provides one unknown pulling in the direction of the cable. Down here at point C was a hinge, and a hinge provides two unknowns. It's an X and a Y. Before doing anything else, you want to take your unknowns and extend their lines of action all the way across the page. And you'll see that we have a few additional points. I will call this point up here B, and I will call this point over here D. I already have points C and A labeled. And now that I've done this, I'm going to need a couple additional distances. I always want to make sure that I know where those points are, and you can really do this at any point in time, but what I typically do is I first draw my unknowns. So I've drawn my support reactions here. This was a hinge, that was a cable at point A. I extend the lines of action, I find where they intersect, and then I find the distances to those points. Now, it may be that I don't actually need to use that point and I don't do the distance, but that's just the way that I typically solve these problems. Now, to find those two distances, I'll need to do a little bit of trig. So I'm going to do that over here in an AuxComp. If I look at the right triangle that has height A, I can see I have a right triangle made here from point B down to this blue line over to point A. The height of that triangle is A. The base is 4 meters. It's C plus E, and it's got a 30-degree angle. So I can say the tangent of gamma equals A divided by C plus E. So solving that for A will tell me that A is 2.30940 meters. Likewise, I have another triangle. Triangle A to this point to point D. That triangle still has a 30-degree angle here, and it has a height of 2 meters. Its base is unknown. Its base is 2 meters plus D. So I can say the tangent of gamma equals the opposite side, which is B, divided by the adjacent side, which is F plus D. And solving that for D will tell me D equals 1.46410 meters. So now I have all my distances solved that I need. The next thing is called an equilibrium analysis. So in the equilibrium analysis, what I'll just do is I'll mentally analyze each of the possibilities. So the first one is I could sum forces in the x direction. And there's no particular order that you have to write these in. I just typically mentally go through some of the forces in the x, then some of the forces in the y. If I look at the x direction, how many unknowns do I have? Well, I don't know F4x. And F3 also has an x component. I don't know F3, so there's actually 2 unknowns in the x direction. The action is do not start. I don't want to start with that direction because there are 2 unknowns, so let's next look at the y direction. In the y direction, I do not know F4y. I do know F1, I do know F2. F3 has a y component and I don't know it either. So my action once again is do not start. So now that I've used both some of the forces in the x and some of the forces in the y, I next need to sum moments around certain points. For example, if I look at point B, F4y goes through point B, and F3 also goes through point B, so the moment produced by those two would be 0, and the only unknown I would be left with is F4x. And the action is solve. Now let's look at point C. At point C, F4x and F4y both go through point C, so the moment produced by them is 0. And the only unknown I'll have there is F3. And my action once again is solve. Now I've found F4x and F3, but I need to find F4y. So I need to find a point where F4x and F3 intersect, and that point is way over here. It's point D. So I can sum moments at point D. And my only unknown there will be F4y. My action is solve. So now I've got all 3 of my unknowns accounted for in the equilibrium analysis. In this table, you need to make sure that you include all of your unknowns. It's really up to you in the order in which you do these, but here's how I'm going to do these. I'm going to start with the point C, so that'll be my step 3. Then I'm going to do point B, that'll be my step 4. Then I'm going to do point D, that'll be my step 5. And then I'm going to check my answer using some of the forces in the x direction. You are required to have a check solution when you do an equilibrium analysis. And for this homework dealing with support reactions, you are required to have an equilibrium analysis. So now we're going to apply static equilibrium to moments with respect to point C. So that would be F1 times D perpendicular plus F2 times d perpendicular plus, now I'm going to break f3 into its x and y components. Plus f4x times d perpendicular plus f4y. Now at point C, you can see that f4x and f4y both go through point C, so they're going to produce no moment. F1 has a non-zero d perpendicular, as does F2. F3's x component's right here, and it has a perpendicular distance. F3's y component is right here. It also has a perpendicular distance, so all of those will have non-zero moment terms. So F1 is going to produce a negative rotation around point C, and its perpendicular distance is C. Once again, it's measured perpendicularly from F1. F2 likewise will provide a negative rotation, and its perpendicular distance is C plus E. F3's x component is right here, and the value of F3x is F3 times cosine of gamma. Its perpendicular distance is B. And if we look at F3x, it would cause this type of rotation around point C. So that's going to be positive. F3's y component is F3 times sine gamma. And F3's y component is here at point A going up. Its perpendicular distance is also C plus E. And it will also produce a positive moment. Grouping like terms and solving for F3 yields this. And plugging our values in, we will find that F3 equals a positive 5.89489 kilonewtons. Don't forget the sign here indicates agreement with the diagram. Next, I said I was going to apply static equilibrium to moments with respect to point B. So that means 0 equals F1 times d perpendicular plus F2 times d perpendicular plus F3 times d perpendicular plus F4x times d perpendicular plus F4y times d perpendicular. So looking up here at point B, F4y goes through point B, so it's going to produce no moment, and F3 also goes through point B, which is why I did not break it into its x and y components. So around point B, F1 is going to produce negative rotation, and its perpendicular distance is C. F2 is likewise going to produce negative rotation around point B, and its perpendicular distance is C plus E. When we look at F4x, F4x is going to produce positive rotation around point B, and its perpendicular distance is A plus B. Here's F4x. From F4x to this blue line is B. From that blue line to point B is A. Solving that equation for F4x gives us this. Notice that I've properly algebraically developed this equation and solved for the unknown before I plug any numbers in. And now plugging the numbers in, we'll find that f4x equals a positive 5.10512 kilonewtons. You'll notice that I assume these forces correctly. There's no problem if you don't assume them correctly. If you end up drawing f4x going to the left and you get a negative sign here, there's no problem at all with that. It just means your assumption was incorrect. These forces I've drawn here for the support reactions, although I know that a hinge or a pin is going to produce an x and a y force, I really don't know which way they're going until after I apply static equilibrium. So the direction that I put on the forces is actually assumed. Next, I'm going to apply static equilibrium to moments with respect to point D. So we start by stating our assumption. So that's F1 times D perpendicular plus F2 times D perpendicular plus F3 times D perpendicular plus F4x times D perpendicular plus F4y times D perpendicular. Looking at these things, F4x goes through point D, so it's going to produce no moment. F3 also goes through point D, so it will produce no moment. Around point D, F1 is going to cause positive rotation, and its perpendicular distance is E plus F plus D. F2 is likewise going to cause positive rotation, and its perpendicular distance is F plus D. F4y is going to cause negative rotation, and its perpendicular distance is C plus E plus F plus D. Solving this equation for F4y, plugging the numbers in, we will find that F4y is a positive 4.05256 kilonewtons. Now we found all three of the answers. We found F3, F4x, and F4y, but part of this particular solution procedure requires that you also do a check solution to make sure that those answers are correct. Now you can check your solution by any static equilibrium statement you have not already used. So in this case, I could check my solution by using static equilibrium in the x, static equilibrium in the y. I could use static equilibrium with moments with respect to point A. I could make a new point here and use static equilibrium around that point. In this case, I used x because two of my unknowns are in the x direction, F4x and F3, and it actually reduces the number of parts to my equation. So we start by stating our assumption. Sum of the forces in the x direction equals 0. And then 0 equals, well, the only forces are F4x and F3x. F4x is a positive F4x. F3x is a negative F3 times cosine gamma. Now I want to point something out here. In this case, my answers agree with the signs in which I've drawn them. If they did not agree, I would need to make sure to account for that sign here. So I would have to change that sign if I got a negative for F3, because although I've drawn it in the negative direction, the negative sign in my answer when I did static equilibrium would indicate that it's incorrect. So just make sure that you're keeping track of that. And there's a number of ways to do that. In this case, my assumptions were all correct, so I could just go based on the diagram, but always go back to the calculations you have. So now I can plug numbers in. And go ahead and plug that into your calculator, and you'll see that it doesn't exactly equal 0. Those two terms don't exactly add up to 0. However, it's very close, and it should be 0 within 4 significant figures. If that is the case, then the next thing you just write is a check sign, or you write the words solution checks. Only do that if your solution actually checks out. If you get to the end of the problem and your solution doesn't check, best practice would be to go back and fix what was wrong. If you don't have time to do it, don't lie and say the solution checks. Just say solution does not check and leave it alone. I don't want to see anyone writing solution checks when it does not check. So then all of your answers go in the answer box, and we have found all of the forces that are supporting this particular object. This is still just utilizing static equilibrium. The new things here are the equilibrium analysis, using this check solution, and being able to go from the initial diagram, which had the supports just drawn in as hinges and cables and things of that nature, to the free body diagram, which then provides the forces that are supporting the object here.